There can be a lot of confusion in these problems about how exactly you go about finding the normal force. So sort of the title of this video here is the normal force is not always equal to mg. So if you're going to walk around and work on physics problems, and every time you see an n, you're just going to say it's mg, you're going to get yourself into trouble because it's not always true. So what I'm going to do is I'm going to show you a couple of cases here where the normal force is not equal to mg and give you a general prescription about how to find it. Okay. So let's just start by looking at the case where the normal force is mg. Look at a block sitting on a flat surface like this, a table or a road. I will agree with you the normal force is equal to mg, but I'm going to prove to you that it is. First thing we know about this block is that there's a weight on it which is straight down like that. And the next thing we know is that we've caused some molecular flexion to occur in here, and so there will be a normal force pushing up on the block like that. Those are the two forces, real forces that are acting on the block. There's the weight down and the normal force up, which has to do with the fact that this block has caused a deformation of the surface like that, and these molecules would like to restore to equilibrium, so they push up on the block. Now, what I know about this problem is that if I read it, is the problem never said anything about this block lifting off the surface. Likewise, it never said anything about the block digging down into the surface. It says the block is on the surface. So if there's no levitation or no digging like that, what I conclude then is that the sum of the forces on this block, say along the y-axis, are equal to 0. And I'll just say that, loosely speaking, this is the y-axis, are equal to 0. Because there won't be an acceleration, and so if the velocity of the block, say either up or down, is 0, and there's no force on the block in that direction, there can't be an acceleration on it, and the block will never rise and never dig down. In other words, we'll just stick with the prescription of the problem. The block doesn't lift off the table, and it doesn't dig down into the road. So if I actually carry out this sum then, what I see here, if I sum the force in the y direction, I'll get a normal force up, I'll get a weight down, and all that's equal to 0, and now I'll have a simple algebraic equation I can solve to say, all right, look, the normal force is equal to mg. That is true. So a block sitting on a flat surface, the normal force is equal to mg. But again, I didn't guess, I didn't write down, I thought about it and said, look, the problem never said anything about the block rising off the surface, digging into the surface, so the sum of the forces on it in the y direction must be 0, and that's where I get the normal force from. Okay. I'll show you another example here where the normal force is not equal to mg. Here's a problem where a block's on an incline. Something like that. What's the normal force now? Well, I showed you another video that had to do with the sliding force that said if you have a block on an incline like this, there's a couple things you can do with the components of gravity to help you get something started. So the only force acting on this block is gravity, which is straight down, and again, because this block is sitting on the surface, you've caused molecular stressing or flexion right in there, so there will be a normal force pushing up on the block like that. So you have a normal force and weight straight down like that. Now, what I showed you also in that other video about the sliding force is that if you sort of complete this right triangle down here, like this and like this component over here, if this is theta, this will be theta in here, this component over here will be mg times the cosine theta, this component over here will be mg times the sine of theta. You have two components of gravity that are acting on the block. So gravity is actually the only real force on the block, but we have two components of it as well. Now, just like in the last example, I can sort of look at this anti-digging or anti-levitation idea to say, hey, the problem never said anything about this block lifting off the surface or digging down into it. And if that's true, then I can look along this axis right here, and I don't know what you want to call the axis. I guess we'll just call it the y-axis or something, because we imagine just a y-axis, like if we rotate the system like that, it looks like a y-axis, but I'll just sort of keep my orientation here. If I sum the forces once again along that y-axis like this, it'll look like this. The sum of the forces will have a normal force up. That's this arrow right here. That's the response to the molecular flexing. But I have a component of gravity down along this axis like this. I'll have a minus mg times the cosine of theta, and there aren't any other forces on the axis, so all that's equal to 0. Now, without doing any guessing or doing anything like that, I've just hypothesized that this block never lifts off the surface and never digs down into it. This must be true here. So what I'll get then, if I just solve this algebraically, I'll get that the normal force is mg times the cosine of theta. And there you go. Here's an example where the normal force is not equal to mg. I didn't just see n and put in mg. I looked back at the problem and said, okay, there's a normal force because of molecular flexing. There's a component of gravity down here because of gravity acting on it. And if the object is not going to rise and not going to dig, the normal force must balance gravity, and that's exactly what happens. So n is mg cosine theta. So yes, for instance, if you were working a friction problem for a surface on an incline, and friction was mu times the normal force, this would be the normal force you put in. This is the primary way students get themselves in trouble. They see an N and just put in an mg, but it's wrong for this problem here. You would put in an mg times the cosine of theta for a problem like this, and that's the reason why. Okay? One more example where the normal force is not equal to mg, and here it is. Here's a block once again, and suppose it's sitting on a flat surface like that, and suppose that someone is pulling on the block this way with a force F. And say that F is being pulled on here, I don't know, some angle theta, anything you want. So it's plausible that someone could tie a rope onto a block and pull it sort of up and to the right like that, and you might want to analyze a particular motion. So the question now, what is the normal force? Okay? We'll proceed as usual and say, well, this whole thing is taking place near a planet, so there's going to be a weight down on a block like that, an mg. And because the block is sitting on the surface, it's going to cause some molecular flexing to happen in there, which is going to result in these molecules wanting to spring back up. They're going to present a normal force on the block, straight up like that. Okay, so there's a situation that you have so far. There's normal force and gravity. So what you have then is the normal force in response to the molecular flexing, gravity because the problem's taking place near a planet, but then you have the person's force that they are pulling on it to go up like that. What is the normal force? If you say mg in this problem, you'd be wrong. The normal force instead comes from a bit of sort of sophisticated analysis here. Let's lift up a little bit and see if we can figure out where the normal force would be. We look at the block. The problem doesn't say anything about the block ever lifting off the surface. Likewise, it doesn't say anything about the block digging down into the surface. That sort of motion up and down this way never happens. If that doesn't happen, then the sum of the forces along the y-axis must be equal to 0. Why? Because the block has a vertical velocity of 0. And if we want that to stay, we never want to start achieving velocity up or down, the acceleration on the axis must be 0 as well. So if all that's going to hold, if the acceleration along the y-axis is going to be 0, there can't be any forces along this axis either, so the sum of the forces must be 0 as well. Let's just sum those forces along the y-axis. I see a normal force up, and I see gravity or weight down. But now because this person is pulling on it, I also see a component of this force over this way, in particular, which is going to be F times the sine of theta, like that. There will be a plus F times the sine of theta, like that. That's another force along the y-axis. And again, if the block isn't going to levitate, all this must be equal to 0. The molecular flexion, the weight down, and the person's pull-up all have to contribute to maintain a 0 force, so acceleration can be 0, and the block can never sort of develop at a velocity up or down off the incline. If I solve this for the normal force, which is sort of the point of this video here, the normal force would then be mg minus F times the sine of theta. This is the normal force. And notice in particular, it is not just equal to mg. It involves mg, but it's not just mg directly. What is actually happening here? Well, if you look at it, the normal force comes from the molecular flexing. How strong do these molecules have to push up to restore themselves back to equilibrium? Well, it has to do with the weight, certainly how heavy the block is and how much weight is coming down on them. But because the person is pulling up and to the right, they're actually lifting on the block a little bit. They're pulling up a bit. So the molecules don't have to flex as much as they would if it was just the weight alone here. So for instance, and that's why the normal force is mg minus that force. So if the block was just sitting here by itself, maybe the molecules in the surface would have to flex down a great deal like that in order to support the weight of the block, way down like that. But if you have the same system here, the block with that person pulling up, the molecules don't have to flex down as much because the person is sort of supporting a little bit of that flexion by this upwards component of the force. That F sub y there is relieving the surface of having to stress as much as it would have here if that upwards force wasn't present. So there you go. Another example where the normal force is not equal to mg. So the moral of the story is to find the normal force here, being very careful with that here. Let's just say we'll do the following here. We look at the problem. And typically here, now I know this sort of maybe is kind of funny here, but looking at the problem is something maybe we don't do enough here. But the problem will not refer to 1. It's oftentimes no levitation. It doesn't say anything about the object lifting off the surface. And number 2, there's no digging. Problems often don't refer to some object digging into the surface as it sits on there. And if this is true then the sum of the forces, I'll say perpendicular, and that perpendicular to the surface, must be equal to 0. And again, why do you want those forces to be equal to 0? Because if there's no levitation and no digging, you always want the velocity perpendicular to the surface to be 0, and if that O is going to be 0, you need the acceleration perpendicular to the surface, O is to be 0 too. And you can achieve this by ensuring that the sum of the forces are equal to 0. So this is the safest, most correct, and robust way to find the normal force in any situation in the most correct manner possible. And lastly, if you walk around and the only thing that you sort of have in your mind is that the normal force is equal to mg, you're going to get yourself into trouble. It is sometimes, but not all the time.